Welcome. In this recording, we are providing an overview and update of the open specification for Analytics Interoperability project, what we have done so far in the project, why is it project important, and this recording also consists of a demonstration done for one of the use cases done in the project. To survive in today's very competitive market, energy organizations need to perform in the most effective and efficient way through the life cycle of a project or an asset. To achieve this, information must be shared across operational areas and across the organizations involved in the value chain. But data about the processes usually exist in organizational silos, and a lack of interoperability of a shared language to communicate the data has caused extensive challenges across the energy sector, similar to the challenges faced by many other sectors. Many companies are now investing in advanced analytical capabilities to remain competitive, but the limited interoperability of both the data systems as well as the analytical methods that could be useful to give the oversight of their processes is severely limiting the sector's ability to gain insights from the advanced data analytics. In this project, we are working towards providing standards-based interoperability for data analytics. So this goes beyond data sharing, and it's letting the analytical and management systems, the software interfaces, communicate directly. Interoperable analytics will allow us to share results between the analysis methods, so we can get a more holistic view of the output produced by different analyses. Interoperable analytics will inform on not only the individual components, but can aggregate to give a picture of the complete system across a range of different contexts, whether it's for reliability, efficiency, or even safety. Being able to combine and integrate results between multiple analysis methods with a system-wide view should make for a better strategic analysis and decision making. We are working towards providing an open specification for interoperable analytics through the 3 years long project funded by the Future Energy Exports CRC, which began in the middle of 2021. In this project, a team of experts from universities along with involved industry partners to identify and pilot high priority use cases for interoperable analytics. We plan to validate the specifications produced in this project for the Queensland University's hydrogen export pilot plant. In the beginning of the project, we identified various types of analytics applicable to different life cycle phases of a plant and consulted the industry partners to identify the highest priority examples where interoperable analytics is needed and will provide the most value to the energy sector and other similar sectors. The first example suggested by the industry partners is using the interoperable analytics for risk modeling and assessment, especially since it is applicable and crucial throughout the life cycle of a plant. During the initial brainstorming within the project team, we identified various aspects that the interoperable analytics framework should be able to support a good risk-based analysis. The risk modeling and assessment framework should be able to consider the 4 dimensions depicted in this diagram. To begin with, the horizontal dimension is where you're assessing one component in different contexts or using different methods. The context here can be safety risk, reliability risk, capacity risk, cyber risks, and so on. The next dimension is the vertical dimension where you're aggregating the individual component risks into the larger system to determine the risk at a system level. So what is the impact of having a fault at a component level over to the system or the system of system risk? The third dimension is the temporal dimension where you are looking at the variation in risk across the entire asset life cycle. So you're projecting the component risk over to the risk towards its life cycle. And the final dimension is the need to incorporate the uncertainty associated with all these risk assessment techniques throughout. So the overarching uncertainty going on the top of the whole diagram. Given the interconnected nature of critical infrastructure in the energy sector, the ability to model, monitor, and manage risks and assess the impact of risk not only on individual component but on the entire connected system and system of systems is critical to avoid the potential for cascading failures. By developing a risk modeling and assessment framework using interoperable analytics, critical infrastructure owners will get a better understanding of the vulnerabilities and dependencies in their own systems and can address those risks to make their infrastructure more resilient. Given the wide scope of the case study 1, we have divided into 2 use cases. Use case R1 deals with development of the risk model itself and continuously improving it based on its usage in use case R2, where in use case R2 you're actually using the risk model and linking various risk models together. The use case R1 describes the process for establishing a risk model which is built upon existing human knowledge and augmented with the data analytical capabilities. While the experience-based risk model captures the knowledge and experience of subject matter experts well versed with the probability of a risk event occurring and its potential impact and severity, the data-driven risk model provides additional evidence-based certainty to the risk model by analyzing the historical data available in one or more fit-for-purpose digital twins representing the targeted systems and its elements. This use case also includes the process for continuous improvement in the risk model based on its usage and associated learnings both during the testing and in practice. The feedback received on the quality of risk events produced from the risk model is incorporated in the model on an ongoing basis. The improvements in the model over its lifetime is also attributed to the insights produced from multiple data analytics running on the current or historical data. The use case R2 describes the process of using the risk model to assess the impact of a risk event and generate recommendations to mitigate the consequence of the risk event. This use case provides continuous feedback to the use case R1, where risk model is dynamically adjusted based on the assessment of outcomes generated by the risk model. This use case also describes the process of linking and cascading different types and levels of risks. For example, linking operational risk with strategic, financial, and other risks provides a holistic or integrated view of the risk across the organizations. To bridge the gap between different levels of risk and risk models, interoperability between systems, models, and analysis methods is required. A risk event produced as a result of the failure or a performance degradation of an asset at operational level will impact the financial risk model because the associated cost with the repair or inspection of the asset, and the impact to the operations in terms of possible downtime or reduced output. The same risk event will also impact the short and long-term strategy of the organization with respect to activities related to planning and scheduling. Hence, the risk events produced from various types of risk models deployed in an organization need to be propagated to other risk models to obtain an integrated risk profile at the enterprise level. The enterprise risk management team should collectively monitor all types of risks that might impact the enterprise strategic success. Hence, the focus of ERM should not only be on strategy risk, but on all other types of risks such as operational, financial, which are important for the viability of an enterprise. This has not been successful till now because there were no interoperable analytics available. The use cases R1 and R2 are documented in the standardized use case architecture published in ISO 18101 as part of the Open Industrial Interoperable Ecosystem OIIE framework, which identifies that to support interoperability across any industry, it is important to describe the use cases in a standardized fashion. By describing the use cases consistently, using specific interoperability concerns can be addressed. For example, the actors involved in the use case would know exactly what is expected from them when they're taking part in different set of interactions in a use case. The OIE use case architecture shown here defines a standardized breakdown of the use cases into smaller reusable parts, where the OIE use cases describe common interactions and context to achieve an interoperability goal and are decomposed into one or more OIE scenarios, where each OIE scenario provides an additional details and requirements on how to achieve an interaction based on a specific group of OIE events. The OIE event provide details of specific message exchanges and their requirements, but are general enough to support different realizations of the exchanges over different protocols and data formats. These three components of the OIE use cases, namely use cases, scenarios, and events, are tied together by user stories, which provides a higher level overview of interactions and connect the use cases in a logical flow. We have done a pilot implementation of the use case R2 to demonstrate its use in analyzing real and complex data systems. This pilot demonstrates the adaptability of the use cases being developed and so that it can be easily adopted by the industry. In the pilot, we have showcased 3 steps. First is where you're populating the baseline data. The second is where a risk event happens, a motor fails functionally. And the third, where you procure a motor to mitigate the impact of the motor failure. In the baseline information population, we are passing across the information about the breakdown structure of the plant, the assets installed, and the function location. So we are making sure all the involved systems in the pilot have the basic structure set up with respect to the structure of the well system being considered here. We'll also show that the operational data coming from the condition monitoring systems, the control system is displayed on the risk dashboard, and we are getting the basic risk information from the risk management system. When the motor 1 fails, which is a risk event happening, the status of motor 1 would change from active to failed, while the motor 2, which is in a standby mode, would become active. And this is the problem now. The impact of the failure and the probability of the well system would increase because there's no standby motor. And we would show on the risk dashboard that the measurements are now coming from motor 2. To mitigate the impact of this risk event, the information should be communicated from the operational risk model about this increased impact and probability of failure to the procurement risk model. And the consequence of that, the procurement risk model should be advising procurement of a new motor on a high priority basis so that the probability of failure and impact of failure of the system comes back to the baseline situation. Once the motor is procured and installed and now available as a standby motor, we are back to the baseline situation where we had 2 motors, 1 active and 1 in standby. But by this pilot, we are demonstrating 2 aspects of the risk model linkages. One is where we are showing that how an impact of a risk event happening at a component level is being cascaded to the system level. How we can show that the failure of a motor and its impact on the whole overall well system. The second aspect is how we are linking various risk models together. A motor failure or component failure is an operational risk model system, while we are communicating it with the procurement risk model so that the overall efficiency of the organization is achieved. In the future pilots, we plan to show linking with other risk management systems, for example, the production risk management system. For example, we can say that if a motor has failed, we may advise changing the production schedule but reducing it to a value so that it can still continue producing but to a reduced amount. In the pilot, we have used a coal seam gas well system, for example, which was provided by the Synenco. The risk information for the well system was also provided by Synenco. We have also leveraged the existing reference implementations of the OI specifications shown here, and these implementations are provided by the Australian OI Interoperability Laboratory based in UniSA. For this pilot, we have specifically used ISBM for messaging and SDR for exchanging the initial breakdown structure information, the asset information, and the functional location information. I'll hand it over to now Mansi and Andrew, who would showcase the demo.
This shows the startup of the risk management node in the dynamic risk assessment scenario. The program has already been told which system ID it needs to monitor and where to listen for event data. This program is going to initially connect to ISBM, and it is going to listen for 3 messages that contain plant configuration information that it will need for tracking the risk of this system.
This screen shows initial baseline data of all sync well system, which includes functional location, assets. A particular assets is pointing to which functional location. So this step is required to populate in process systems such as risk dashboard, risk management system aspect to fill the baseline information. So there are basically 3 events which we are publishing to ISBM. First is sync assets, second is sync segments, and third is sync asset segment events. So let me just publish it one by one. So it's published. So the second one is sync assets. So I'm publishing it now. And third is sync asset segment events. So that's also published.
The first message that will arrive will be a sync segments message. And here it is. And the sync segments message is going to tell us information that we need to know about the unique identifiers of functional locations and the plant component structure and the human readable names of all of these plant design components. The next message that is going to arrive is going to be a sync assets message. And here it is. And the sync assets message is going to tell us information about the assets that will be installed in this system and their status. The next message that is going to be arrived is a sync asset segment events message. This type of message tells the risk manager which functional locations these actual events are, actual assets are installed in. After receiving the first three setup messages, this risk manager now has all of the information that it needs to publish its first baseline risk assessment of the system. This is published in a sync actual events type of CCOM XML message. The message is in a standard format, though with some custom attribute names that we use to represent the risk of a failure event. And this includes things like impact, probability, and the context that the assessment applies to, such as the time range. We can also look at the contents of one of these messages. We will see that there are three actual event elements that are all bundled into the one message. We can then search for the well system to try to find that, and we'll see it's at the third actual event in the message. And we can do some more searching to try to find the Australian dollars figure. And that will show us the impact that has been assessed as part of the baseline risk for this system. Having found that, this is the assessed impact of a failure on the system if it occurs. This message is the baseline risk of the system, which has been published on ISBM. Our risk manager node will keep listening for other events that will change the risk of this system.
So now, let me just give some information about the risk demonstration dashboard. So this is the dashboard that's showing different parts of the this well system risk and the motor 1 and motor 2 status information and other information about how the motors are working, what's the vibrations are. So let me just go each section one by one. So these two sections are basically for showing the motor status. So it's active, standby, failed. So that's showing that status with the vibration information. After that, we can show that we can see that that's alarm section that's having the number of components counted. So there are when any motor fails, there are some issues detected in that motor. That issues will be shown here, and that number of issues will be counted and displayed in the alarm section. The next section is about the vibration information, which is live updating the information every 3 seconds. So that's changing every 3 seconds, and that's from the dynamic vibrations that's generated by M1. And when M1 failed, then the vibrations will come from the M2. So this is similar to the breakdown structure. So it's the showing the risk information of motor 1, motor 2, and valve system as a whole system, like what's the risk, what's the probability confidence, what's the impact, what's the weighted risk in the Australian dollars. So this will change based on the when motor 1 fail or any motor fails, then the risk will be higher because we don't have any standby motor left. So that this section will also change dynamically, and this is the live update section. That's the adding whatever the events we are calling that's adding into the list, and it will be shown here. So we will get idea that's what's exactly happening. And this is the component issue section. That's is there any issue with the motor, then it will show the messages here. So let me just start by receiving the baseline risk information. So let me just refresh the dashboard, as we can go to the first point where there is normal vibrations for motor 1 and everything is going right, but suddenly the vibrations are starting to increase. And right now we are seeing the baseline risk information, which is now coming from the ISBM, and that's the updating the dashboard as well. So this is the baseline risk information that's we received, and it's currently not much high because we have standby motor left and we have one motor that's actually active now. But now we can see that the vibrations are increasing and it's fluctuating. So it's continuously increasing. So now we are publishing the failure event. So that's changing the status of motor. So that's the basically triggering the high vibrations, and these are the messages that's coming from the motor, like the issues of motor 1, and that will change the alarms, like the counts of the issue components. Still the vibrations for motor 1 is increasing, as we can see. So now it will be failed within some time. So we are publishing the event for the motor 1 failed. So now it's a motor 1 failed, so that will change the color of the risks as well, that the M1 is failed, M2 is still not active, and our whole system is like in the warning state. And so there is no vibrations for the M1 right now, so it's just the similar. And as we can see, that's the whatever the events are triggering, that's adding into the live section, live update section. And we still have that issues with the motor 1, so it's showing the messages that what's happening.
The next message that will arrive will be a sync actual events message. This particular event indicates that a high vibration has been detected on motor number 1. The only use that the risk management node has for this message is that it is going to refer to it later as supporting evidence in a future risk assessment. So it won't take any action on this event, but it needs to remember this message because it relates to a segment of the system which this risk management node is trying to track the risk about, and so it may become useful later. The next message that has arrived is another sync assets message. This particular message tells us that the operational state of a particular asset has changed. We now know that asset motor number 1 has failed, which implies that functional location M1 has failed. This will have several effects. Firstly, it starts a countdown timer, which is going to be used to suppress the publication of risk assessments for a short period of time that matches the expected failover time of this pool of redundant motors. And this is so that it does not issue a bad risk assessment when we expect that the control system will fail over to a good motor, which is ready and standby. This status event also causes the risk manager to reassess the risk of the system. However, because of the timer that's currently suppressing publication, it will not publish this new risk yet, and it will continue waiting for more messages.
Now, as we have another motor there, so we will turn it on. So we are publishing event that will active the motor 2, and that will change the status, and then the vibrations are now coming from the motor 2, and it will normal. It is currently normal and it's working in good condition, so it's normal vibrations, and that's everything is going good. So M2 is now active, so it's in green color, and M1 is still red. We don't have any the additional system, additional motor left, so still we are working on just one motor. So the valve system is still in yellow color, so which says it's in still warning state. and still it's the live updates. It's updating by calling the measurements and other live updates. So now we are waiting for the risk information.
The risk management node has received another sync assets message. Now the message tells us that the motor in location M2 is now running. This is good news, as it means that the failover has happened exactly as we expected. This also means we can now cancel the countdown timer that was previously preventing the publication of risk. We will also set the new statuses of the related segments in our risk model, and we can then rerun our risk model to get our new system risk now that M2 has taken over the load, but it does not have any backup motor. So this will cause another sync actual events BOD message to be published with our revised risk assessment.
It shows the impact is very high, and suddenly the risk of the system is increased because we don't have any motor left. And now we can see that the system having higher risk and higher impact in Australian dollars. So now we are triggering the next event, which is active the we are assuming that the motor 1 or like motor 3 is replacing the motor 1, and which is repaired, and now it's like going to install, and that will be available. So we are publishing the next event, which says the motor 3 is now available on a standby mode, and the vibration are still coming for M2, and that's the active motor, but we have the M3 motor is still there, so we have that motor is as an additional motor. So it's the same way the live updates and component issues, so we don't have any issues now. So with the motor 2 and even with the motor 3, so it's the same, like the functional location is the same M1, but asset name is the motor 3.
Several messages have been received. The risk manager has received another sync assets message, which tells us that there is a new physical motor installed in our system. We also receive another sync asset segment events message, which tells us that the new motor number 3 has been installed in the location M1 where the old failed motor used to be. The next event we receive is another sync assets message. This changes our operational state information about motor number 3. Functional location M1 was where the old motor failed, but the new motor asset installed at the same logical place has now taken over the load. This again causes a change in the assessed system risk, which is above the reporting threshold, and so it will now report a new system risk message. And you can see in the log that it has published. It has published this message as a sync actual events message, and it will be in the same standard CCOM format that we saw before.
Now we are getting the risk information that will be similar to the initial state. That's the low. That's actually the lower risk because we have standby motor left. So this is the whole demonstration of risk demonstration dashboard.
The risk manager node continues to listen for other events. However, now that we've solved the incident of the failed motor, that's the end of this scenario, and so it will not hear any more events in this demonstration.
Thanks, Andrew and Mansi. The primary benefit for the open specification for interoperable analytics is for the asset owners and operators to take advantage of the higher quality decision making based on more holistic view and analysis of their operations. By developing and demonstrating these open specifications, we are aiming to move analytical systems from ad hoc bespoke implementation to a standard-based interoperable model. The industry will be able to adopt more holistic analytics on a supplier-neutral basis, avoiding vendor lock-in and accessing best-of-breed solutions with significantly reduced cost and risk. We are achieving this by leveraging the Open Industrial Interoperability Ecosystem Framework led by Mimosa and published in ISO 18101, which provides a standards-based interoperability framework between different types of systems in industrial environments and between different industries in the energy value chain. Thank you for watching this recording.